joining today's webinar organized by Southern Plain Transportation Center in association with Accelerated Bridge Construction from Florida International University, and also another partner is Oklahoma Department of Transportation. Um, so, as you know, Southern Plain Transportation Center uh, organizes SPTC webinar series. Southern Plains Transportation Center recently got a US DOT funding to establish a regional university transportation center at University of Oklahoma. And we have a consortium member of 11 universities.
Yeah.
So we would suggest all of you to mute yourself when you join, so that like we can have an uninterrupted webinar session today. Uh, I'm sorry, like we can hear some noise, so it will be we will appreciate if you kindly mute yourself. All right. So SPTC organizes the monthly webinar, short courses, and workshops on a regular basis on recent and emerging topics to serve the transportation community as a part of its workforce development goal. Uh, so today, as a part of this, today we have Dr. Henry Liu from University of Michigan here with us to give us a presentation on safety assessment of highly automated vehicles. Before we start with this webinar, uh, uh, let me give you some notes on housekeeping. Please, we will request all of you to mute yourself. If you want to keep your camera on, that is completely okay with us. Also, if you have any question, please post your question in the chat box. We will communicate all the questions at the end of the presentation to our speaker. And also, we request you to use your name that you have registered with in this webinar, so that we can track your attendance and provide you with the PDH that you want. And also, this session is being recorded, and we will upload the recording and the slides of this presentation, PDF of this presentation, in our SPTC website. So with that, we are going to start with the presentation for today. So before we do that, let me give you a little introduction of Dr. Henry Liu. Dr. Henry Liu is the director of MCT and Bruce D. Greenshield's Professor of Engineering at the University of Michigan, Ann Arbor. He also directs the Center for Connected and Automated Transportation, which is also a US DOT-funded regional university transportation center. Dr. Liu's research interest is actually multidisciplinary at the interface of transportation engineering, automotive engineering, and artificial intelligence. He is recognized for his foundational work in cyber physical transportation systems, particularly on the development of smart traffic signals systems with connected vehicles and or testing and evaluation of autonomous vehicle. He is a very active researcher with more than 130 journal publication, and also his work was featured in Nature and was featured as a cover story in Nature. So that's a very good achievement. Actually, we really appreciate your work, Dr. Henry Liu. And he also appears in the public media very oftenly to promote smart transportation innovations. He also served as an managing editor of the Journal of Intelligent Transportation System, and also a board member of the ITS America. With that, I want to give the microphone to you, the stage to you, Dr. Henry Liu. Thank you for joining with us, and please proceed as when yeah, please go ahead. Thank you. You are muted, Dr. Liu. You are still muted, Dr. Liu.
Can you hear me now?
Yes, we can hear you now. Yeah, thank you. Please go ahead whenever you are ready. Thank you.
Okay, all right, okay. All right. So thank you, Dr. Ali, for your introduction. What I like to talk about today is on the safety assessment for highly automated vehicles. Before I start, I'd like to introduce the two organizations, two research centers I'm leading. One is MCity. MCity is a research unit at University of Michigan to support faculty and student research, and we are a public-private partnership. And I listed some of our current leadership circle members, including some of the OEMs and tier one suppliers and AWS as a computing platform service provider, cloud service provider. And interestingly, we have State Farm as an insurance and Covington as a law firm related with mobility as well. And I'm also leading Center for Connected Automated Transportation, which is the US DOT UTC, regional UTC. We are Midwest, and most of the Big Ten Midwest schools are part of this UTC. So we have 9 consortium members, and we also closely working with the government, including US DOT, National Science Foundation, our state DOT as well. And so obviously both centers has a mission on research, developing prototypes for instrumentation. Particularly, we instrument the city of Ann Arbor as our test bed. And we also have a closed test track called MCity test facility, which I'm going to talk a little bit on those. And being at the university education outreach also very important to us. And so MCity test facility was built in 2013 and 14, and we were open for operation in 2015. This is also a partnership between U of M, MDOT, and also our industry partners. And so U of M dedicated 32 acres of land, and MDOT provided the funding for us to design the test facility and also for the construction. And all of the facility in terms of the hardware equipment at the facility were donated from the industry partners. And this is also the world first purposely built proving ground for connected automated vehicles. And since 2005, there's many other testing facility available around the world. Many of these are similar to MCity's and built upon MCity's experience as well. And at the moment, we are one of the test facilities, I would say, has the most advanced testing capability for connected automated vehicles in the world. So with that, I'm going to introduce my agenda today. I'm going to talk a little bit related with safety challenge for autonomous vehicles. As you know, autonomous vehicle has been really hot topic in the last 10 to 20 years, but we don't have any commercial available autonomous vehicle yet. And so I'd like to discuss with you in terms of my understanding what are the most difficult challenge for autonomous vehicle technology. And then I'm going to talk about how we assess the safety performance for autonomous vehicles. And MCity has developed 2 part safety assessment program. One is we call autonomous vehicle driver licensing test. Another one is driving intelligence test. And the first one, the licensing test, is focusing on more basic behavior competency test. And the other one is trying to give you more comprehensive in terms of safety performance. Then I will move on in terms of the future MCity development in terms of our test facility, particularly focusing on MCity 2.0. Which we started this project last year. So I'm going to start with autonomous vehicle safety challenge. And this is a news article coming from Business Insider's Intelligence in 2016. And as you can see, that at the time, they predicted that will be 10 million self-driving cars on the road by 2020. And that it's a combination of multiple auto OEMs at the time. And we are almost the end of 2023. We do not have any commercial available consumer level type of highly automated vehicle yet. So and that's why last year October, and this is Fortune magazine has an article describing a long cold winter is here for self-driving cars. And if you track in terms of the development for autonomous vehicles, and there's recent news related with cruise automation under GM, and they have accident occurs in San Francisco, and involved with a pedestrian was actually the accident was initiated through a human-driven vehicle, but and then brought the pedestrian into the pathway of automated vehicle and with contact, and after that, cruise vehicle also, when they pull over, they also drag the pedestrian about 20 feet also. So there's an investigation on the technology, and Cruise also suspended all of their autonomous vehicle operations nationwide. And so, as you can see, there's a lot of roadblocks for the deployment with autonomous vehicle. And if you also are familiar with this technology around the globe, in the last 10 years also, there are about $200 billion investment on this technology. So it's very hot topic, and a lot of companies and also academic institutions working on the technology development and testing. So the reason behind this, obviously, is related with safety. So the safety performance is still not as good as we've expected. And if you look at it in terms of human driver performance, in the US, it's roughly about, including everything in terms of highway driving, urban driving, trucks, and passenger vehicles, the accident rate is roughly about 500,000 and to 1 million miles. But that includes everything. And there's a lot of deployment, trial deployment now, testing in the US, and particularly in California. And so as part of this California DMWIS permit, and if you deploy your vehicle in California, you have to report your disengagement. The disengagement means for this particular contest means the safety drivers interfere or cancel the automated driving function. So the disengagement rate is sort of an indicator of the safety performance as well, but it's not, it's not the accident rate certainly. And so if you look at it in terms of the disengagement rate from the California report, it's about 10,000 to 100,000 miles, depending upon which company doing what testing. And so you can see the gap in terms of the safety performance between automated vehicles versus human drivers. And so we have spent so much money on these, and what are the reasons we still have such safety performance issues with automated vehicle? So I summarize in terms of the safety challenge into two curses. One, I call it curse of dimensionality, which is well known. The curse of dimensionality problem is really when a problem size of the problem of dimensionality increase, the volume of the decision space increase so fast that the available data become very sparse. And so if you look at it in terms of the driving environment, there's multiple factors affecting driving environment. There's weather conditions, there's different type of road infrastructure, there's obviously different type of road users, and each of the users have different behavior as well. And so if you combine all these things together, the driving environment could be very complex. Well, the good news is that in the last 10 years also, there's deep learning technologies being developed. And that when that was emerged in 2013, around 2013, and when you have a much larger network, they can handle very complex problem. And so that's why at the time in 2015, 16 years, people are very optimistic that the scientific challenge for autonomous vehicle technology development essentially is solved, and then so this curse of dimensionality problem is being pushed aside, and that's why people think that the remaining part of this technology development is more or less is on engineering development, and so that's why people has been predict that in a few years also there will be many autonomous vehicle available commercially. Well, during the development, there appears there's another important safety challenge, which was not expected. I summarized this into what I call curse of rarity. And the basic concept of curse of rarity is that if you look at it in terms of safety critical events, in terms of near misses and conflicts, or sometimes in terms of accident for vehicle conflict, then the occurrence probability for this type of event is so rare, and that most of the data you collected from your trials contains little information related with this rare event. And so if you look at it in terms of normal driving situation, the occurring probability versus safety critical near miss, and also the accident, and so the occurring probability drops tremendously. And so that's why this also called a long tail challenge, because the event you are interested, you want autonomous vehicle being able to handle are very rare. And in order for autonomous vehicle, a machine learning agent to learn those, the development cost, the data collection cost, is dramatically increased as well. And so that's why this issue become much more difficult to handle. And I also want to mention this similar challenge exists for other safety critical autonomous system as well. There's medical robot, there's aerospace autonomous system, to a certain extent, the battery management for electrical vehicle as well. And so they all suffers the same type of issue related with so-called curse of rarity, as I summarized. And so if you look at it in terms of the overall safety challenge for the most difficult safety challenge for autonomous vehicles, both these two curses exist. And even worse, the rarity of this safety critical event occurs in this high dimensional driving environment. So the curse of rarity actually compound with the curse of dimensionality. I think that's the root cause for various safety challenges in the development and deployment of autonomous vehicles. So now, not only you need to have the deep learning network to handle complex driving situations, you want your AI agent to be able to handle the small probability safety critical event as well. And so far, the current deep learning algorithm cannot handle this type of cases. And that's also why I think the safety performance for autonomous vehicles are inferior to human drivers in general. And so that's why we don't see commercial level of these autonomous vehicles appear on the market at the moment. So with that, and that's why I want to discuss with you why this is so challenging, and also then in order for us to move forward in terms of this technology, we need to be able to validate their safety performance. So validation of safety performance is very difficult, and turns out this issue related with safety validation itself also suffers curse of rarity as well, because in order for you to validate in terms of his safety performance, if you do compare that with human drivers, and to prove autonomous vehicle are 20% better than human drivers, if you use a fleet of 100 autonomous vehicles, and on average, if they drive 25 miles per hour, if you want to validate that, then you will need to validate that performance. If they can do better job in terms of avoiding crashes, that you need 28 million. And if you compare that with avoiding fatalities, then you need 5 billion miles. And this is a result coming from this paper published in 2016 and 17 from Rand Corporation, and they look at it in terms of if we need to validate, how much effort we will need. And so obviously this is, it's unbearable in terms of even for us to validate the safety performance for autonomous vehicles. And that's mainly because of the cursor rarity I was talking about in the last slide. And so if you look at it in terms of the existing testing method, there's three major type of testing methods. One is in simulation, another one is the test track like MCity, and the most obvious one is just to deploy your vehicles on the road, on public road. And if you deploy on public road, then obviously is very costly and time consuming and it's expensive. And if the technology is not mature enough, deploying on the road could become a public hazard as well. And so that's why a lot of these testing actually occurs in simulation and to a certain extent in the test track as well. And both simulation and test track has advantage and disadvantage. And obviously the simulation to get to reality gap is a real concern for utilizing simulation to validate the safety performance. So the fidelity of the simulation. And then if you want to validate that in the test track, just like MCity, then a major difficulty is that the closed test track usually has no background traffic. You don't have other vehicles, and so you usually can only test very simple scenario-based cases. And so those are the issues, related with simulation and test track, and I'm going to talk about what we have done to improve that and to solve some of the problems. So our approach to validate, the machine learning based autonomous vehicle driving agent is to develop these what we call intelligent testing environment. So our argument is that in order to test the safety performance for the intelligent agent, we also need to have an intelligent testing environment. And so you will need to put your machine learning agent into really intelligent environment to test it. And so so that's our argument. So our focus will be utilizing the data we collect from the field to construct an intelligent testing environment. And so that's why we have developed what we call safety assessment program. And both of these are based upon the machine learning algorithms. And so for safety assessment program, we have a two-stage test. And one we call driver licensing test, is just like human drivers. Before human drivers get a license, they will need to be tested by a tester. And to test your basic behavior competency and whether you can, follow other cars, whether you can do the lane change, merging, and navigating through the intersections and things like that. So we want to do similar test for computerized drivers for autonomous vehicle as well, and based upon their operation design domain, and then based upon the data we collect from the real world. The second part of this is to provide a test so that we can get the comprehensive performance evaluation to specify really what will be the occurrence rate for accident occurs for these autonomous vehicles, particularly in comparison of a human reference driver in the naturalistic driving environment. So we have this two-stage testing process, and I will mention what we do with these two stages. So the driver licensing test is based upon a technology we have developed over the last few years at the MCity. We call it ABC test. And so focusing on really, we need to accelerate in terms of the parameter selection, because even for a simple scenario test, if we want to validate these, we need many miles. And so we want to be able to accelerate the evaluation. And we want to focus on basic behavior competency based upon a set of scenarios we have developed, and we have a scenarios library. And for many of the autonomous vehicle companies, their scenario library is huge. They have tens of thousands of scenarios within their scenario library. And all of these scenarios, for each of the scenarios, you need to select the parameters based upon their naturalistic driving environment. And for our ABC test, we also want to explore what are the boundaries of their, driving behavior competency. So we want to examine in terms of these corner cases or these long tail events we just talked about. And so all of these are based upon naturalistic driving data, and there's a set of open source naturalistic driving data, and MCD has their own open source data as well. And so the data we have been utilized for driver licensing tests is from ArgoVerse data, and that's from Argo AI before. And from that data, we have a set of scenarios we have developed. And then I'll show you a few of the scenarios, for example, pedestrian crossing. And there's a few parameters. And for example, the distance between the vehicles and pedestrian is one parameter. And also the vehicle speed is another parameter. And then utilizing the naturalistic driving data we collect from the field, we build these stochastic models. And then according to the possibility of resulting into certain crash, then we divided the testing into three different type of tests. One is easy test, easy scenarios, and then medium hard scenarios and hard scenarios. Then we utilizing important sampling technique to accelerate the testing to select these parameters so that we can quickly evaluate their performance on those specific scenarios. And we do this for each of the scenarios, for example, cut-in scenarios, for left turn scenario, and things like that. Just to give you some videos in terms of how we conduct the test. When we do some easy scenario testing, we can also test this in MCD, utilizing background vehicle, and then utilizing a vehicle with automated driving system. So this is testing a vehicle driving through the intersection. There's another background vehicle turning left, and see how this autonomous vehicle react to it. So you can see these scenarios are usually quite simple in terms of the parameters we can change, and then based upon their operation design domain. As I mentioned, the focus here on the driver licensing test is to focus on their basic behavior competency. We want to make sure they can follow other cars, they can do the left turn at the intersection, and they can do the merging and things like that. And then the second part of it, we're trying to provide a more comprehensive evaluation of the driving intelligence test through the driving intelligence test. And again, we're focusing on naturalistic driving environment. And so for this test, a lot of these is based upon simulation and also the test track testing. And then so for us, as I mentioned, there's two issues we have to describe. And so the scenario become much more complex, right? So now not only you have just one background, vehicle, you may have multiple vehicles surrounding the automated vehicle. The scenario could be much more complex. So we need to resolve, again, two issues. One, we want to make sure this environment, naturalistic driving environment, is as realistic as possible, and so that we can produce unbiased estimation of the accident rate. And we want to be able to also accelerate the testing process and to get the measurable occurrence rate in terms of safety performance as quick as possible as well. So we need to solve these two issues: the bias is an issue, and also the efficiency of the testing. And so we leveraging, we want to look at existing naturalistic driving environment simulator. And there's a set of simulator has been developed, particularly in transportation engineering. There's, a macroscopic traffic simulator has been developed over the last 30, 40 years. And AV developers also develop these, simulators and utilizing the data they collect from the field. And so there's two major approach existing. One is, if you collect the data from the field, you can replay the log data, right? So you can replace one of the vehicle by your autonomous agent and see whether your autonomous agent can behave differently and to avoid some of the safety critical situations. Well, the problem with this is usually the other agents is, they follow fixed trajectory, so they are not reactive. They're usually not scalable because they, this just rely upon the log data they have. And so the efficiency of the testing is very limited. And on the other hand, there's for the simulation tools, either based upon the open source simulation or some of the commercial available microscopic simulation, they usually based upon some of the simplified rules, and then it's hard to generalize. And as I mentioned, the focus for us is really to test the safety performance, right? So for safety performance testing, a lot of these focusing on the situation that it's really hard to describe in the, just the simple car following or lane changing rules. For example, if you have a vehicle stop at the roadside, but covering partial of the lane, human drivers probably will navigate nudging through that. But it's hard for the current heuristic rules to do something like that. And as I mentioned, the simulator is also very critical. The modeling of the naturalistic driving environment is very difficult. It's very, very important because they give you the estimation of the accident rate is guiding how you deploy and develop your autonomous vehicle technology. I just want to show you one example. For example, in a roundabout situation, this is a real roundabout in the city of Ann Arbor. And if you look at it in terms of the vehicles in between, this vehicle is approaching to the intersection. By the way, these green bubbles, these are our predicted trajectories when we collect the data. And so if we model in terms of the distance between these two vehicles and at the roundabout when the vehicle approaching to it, then if the real world data shows the distribution that does, and the simulated data shows distribution that does, and when the vehicle get closer, they may get into certain collision, right? And so the collision rate will be very different compare your simulation versus the real world. Then that may mislead your development. If you develop this according to the simulation, you might, because you think the accident rate is lower, and so you might get more aggressive in terms of your autonomous driving strategy. And so that's why the accuracy of the naturalistic driving environment simulator is very important. So that's why we have developed our what we call neuro NDE. It's based upon deep learning transformer-based framework. And what we have done with that is not only just the deep learning network to predict in terms of the future trajectories, short-term trajectories, but also looking at a controllable generation of the accident or near misses. So that's why we have this safety mapping network. Basically, some of the accident or some of the potential accident occurs coming out of this behavior modeling network. Some of these may be realistic, some of them may be not realistic. For these non-realistic safety critical situations, we utilizing the safety mapping network to correct some of these behavior. And then we train this and we design this some loss functions so that we can getting real data and then to train this network to generate the simulation. And they can run this for a long time and then get the naturalistic driving environment simulation model. And this is a paper we published earlier this year at Nature Communication for more detailed description on this. And the data we rely upon is based upon some of the other US DOT funded project. And so this is one of the project we call Smart Intersection Project. We're instrumenting about 21 intersections in the city of Ann Arbor. And then with roadside perception system and also cellular V2X technology. And so this is one of the roundabout we have deployed and with 4 grid-smart cameras and then we fisheye cameras, and then we do object detection tracking, and then we do prediction as well. And as you can see, it's superimposed that into the Google map and give you in terms of the trajectory of the vehicles. And so we use this trajectory to train the machine learning model. And so more importantly, not only we want to be able to, regenerate in terms of nature, the normal driving behaviors, because our focus is focusing on the safety performance. So we want to be able to generate more realistic events as well. And we have installed these cameras for this particular intersection for 2.5 years already. So we have more than 2 years of data. And then also Michigan DOT and University of Michigan's Transportation Research Institute also contract with Michigan DOT to work with them to get all the police reported accident occurs in Michigan into that portal. So every for now we have the accident police reported accident from 2022 and before, and so we can now, since we have deployed our system in 2021, so we can actually validate our object detection tracking through some of the accident occurs at the intersection. So this is one of the accident occurs. I want to replay it for you and verify it with the police report. So you can see the accident occurs. And more importantly, although we can validate this through police report for accident, but we're not able to validate these near misses. But the data we have can collect those. And so you can see that there will be a near miss occurs over here, but there's no accident, so there's no police report. We want to be able to generate this type of situation, not only include the crash, but also the near miss situations. And so this is the video I want to show you from the neural NDE model we developed. We can generate all these type of accidents and also the near miss events. And so not only this is side swipe accident, and there's also other type of accident being generated through the simulator as well. And so this is another one and occurs through because of these vehicles. And this type of event that can be generated through the neural NDE simulator as well. And so there's another, just to show you multiple type of accident. This is a rare end accident occurs, and then it can be generated through the simulator as well. Okay, and so I'm gonna move on. Then we have neural NDE to help us to reduce the simulation to reality gap. And the other issue, as I mentioned, is to make it as realistic, as fast as possible in terms of our evaluation of the accident rate, right? So what we have done is we develop a deep learning model again to train some of the simulated agent to select a moment in terms of at what time, which agent doing what maneuver, and how, what in terms of what probability they take and to challenge automated vehicle. And so we train this through a machine learning model, and to accelerate the testing. What we like to know is in terms of the accident rate, right? So using a much smaller number in terms of the testing miles. And the technology we used is what we call density reinforcement learning. And so I think it's much more complex. It will take a while for me to explain. But in a nutshell, what we're trying to do here is that we will condense the safety critical data to train the background vehicle, and so that these background vehicle will be able to know at what moment take what maneuver with what probability to challenge automated vehicle. At the same time, when we purposely generate these type of challenging situations, we want to be able to convert back into naturalistic driving environment. So we don't want to lose the unbiasedness from the naturalistic environment simulator. And so that's the density reinforcement learning has been developed. And that's the paper we have published in Nature and featured as the cover story. And so that's provide a methodology so that AV developers or even the regulators can quickly evaluate the safety performance for these autonomous vehicles. And so just to give you some more in terms of what type of event could be generated, and this is through our simulator feed into the Kala open source simulator. You can see these. This vehicle is this automated vehicle these red colored vehicle or red boxes vehicle, those are the vehicle we call principal other vehicles, and those are the vehicles being selected at the moment to take some maneuver to challenge automated vehicle. And so you can see that this is another one. So this is a lane merging conflict occurs at this situation. So this is another one example that some type of accident could be occurring, and then with these type of challenge and see how automated vehicle react to it. So there's multiple examples was generated. So as you can see, there are multiple vehicles and could be running this for a long time and essentially give you the accident rate of these vehicles. And we also test this in the test track, not only in simulation. And so MCD has a set of highly automated vehicles we call MCD Open CAV, and they have similar setup in terms of the sensors. Also with open source automated driving system, which we use AutoWare, and we have both versions of AutoWare AI, and AutoWare Universe based upon the robotic operating system. And with that, we also do mixed reality testing. And so, as I mentioned before, we have a test track, but it's empty, right? So now we can use simulation to generate virtual agents and feed that simulated vehicle to automated vehicle as well. And so on your left-hand side, this is our simulator. On your right-hand side, this is our vehicle running in MCD test track, and then we can superimpose these virtual vehicles into the video image inside of the autonomous vehicle, and so the autonomous vehicle, they have to interact both the real world infrastructure, but also the virtual agent generated from the simulator. And in the middle, this is the robotic operating system visualization. The black one is the real vehicle. All the boxes, these are the agent they have to be able to interact. So you can see that in one of the testing situations within MCD. And so for ours right now, we have tested the open source operating automated driving system, the AutoWare system. And we're also working on another US DOT funded project to deploy autonomous shuttles in the city of Detroit for elderly population. And then the city has already selected May Mobility as the autonomous shuttles provider. And now we're working with May Mobility to test their autonomous shuttle, and as we speak. And so we started our testing in October. This test for both part 1 and part 2 will continue through roughly around February of next year, and the report will come up later on with our testing through the MCD Safety Assessment Program. So that's in terms of our safety assessment technology, and as I mentioned, MCD is the world first testing facility for autonomous vehicles. And over the last 9 years, also this facility has been open for operation. Half of the time it will be utilized by industry members, and half of the time by our academic users. And so last year we started a new project for MCD 2.0, and this is a project funded through National Science Foundation. And we're gonna grow MCD through a testing facility into a makerspace for mobility innovations. And in particular, what we like to develop is to develop a set of digital infrastructure on top of the physical infrastructure we have developed, and then make it our mixed reality testing environment available remotely. And so if you at Oklahoma, you don't have to come to Michigan to do the test in MCD. You can test your algorithm in your desktop as long as you have Ethernet access. And so so the key for us is to make this facility available not only to ourselves locally, but also open up the facility nationwide for testing purposes. So from a researcher's perspective, what we like to see is if you have a research idea, as I mentioned, we have other USDOT grant for us to instrument the city of Ann Arbor with roadside perception system and also the CV2X devices. And we have collected data, and we have already made partial of these data available. And we also develop our data engine, which we will convert these raw data into the useful format so that researchers can easily use those. And then we have developed our simulation model based upon the real data we collected from the real world. And we offer those through the cloud services. And then so you can run your scenarios within our simulations through the AWS cloud. And then also the mixed reality test environment in combination of the simulator with the physical facility, and then eventually help you to publish and commercialize. And so, as I mentioned, simulator is a very important piece of it. And in our simulator, we base upon a Sumo open source simulation model. And then also the simulator is running on the cloud. And so we have a middle layer connect to Sumo. And so we replace Sumo, the heuristic driving behavior model into our naturalistic driving environment simulation model, and also our naturalistic and adversarial driving environment model. And so we also connect our simulator with to the physical facility through the MCD-OS. This is a middleware connecting the digital infrastructure with the physical infrastructure. So if you are a remote researcher, you can run your own algorithm, whether it's a perception algorithm or a motion planning algorithm. Then we will provide this API, and then to access the simulator, and then also access to the real facility, the testing facility. And then you will be able to send out your control command to the real vehicles in the test facility, so that you can test out your algorithm through this mixed reality testing environment. And so we have developed we aim to develop a set of use cases, and we are second year into that project. The MCD 2.0 is a 4-year project. And then the first year for us is our internal development. The second year is we aim to develop about 5 use cases. And this is the first use case we have already developed. And we were working with a researcher in Purdue University, and they were running this is their desktop video recording. And then so they running their own motion planning algorithm on their desktop. And then we have our MCD vehicle running within the MCD test facility. And so this is the onboard video camera. And this is the MCD facility camera you can see from the infrastructure perspective. And this is the sort of essentially monitoring what's happening with that vehicle and the surrounding traffic. And this is Sumo simulation. And the red box is the real vehicle controlled by Purdue researchers on there through their algorithms. So if we run, and so you can see the real vehicle is actually running in the test facility, and you can also see this vehicle is being seen from infrastructure, and then you can see this vehicle is running, and there's surrounding vehicles generated from the simulator, and the vehicle is running in the test facility as well. And this is the latency from Purdue to the real vehicle, and so it's roughly about 130 milliseconds or so. So it's acceptable for us. And as you also see, this is actually a virtual. In a couple of seconds, you will see actually a virtual accident occurs in this moment, and one of the vehicle actually doing the cut in, and so this vehicle actually bump into the background vehicle. So this is a real vehicle collide with a virtual agent, and so that's why we can test those through this mixed reality test environment, make it safe for testing as well. So the last thing I want to mention is, so I was talking about in terms of what in terms of safety challenge for automated vehicle, in terms of how MC addressed this one piece of it in terms of safety validation, and also what are the testing facility, the next generation testing facility we're working on through the MCD 2.0 project. One of the things when I present this at the university, particularly to civil engineering and transportation program, I like to use this slide. It's because what we have seen in terms of this autonomous vehicle technology development, a lot of work has been done through robotics field, and also from the computer science, artificial intelligence, and also to a certain extent mechanical engineering in terms of control system as well. Not so much from civil transportation researchers. A lot of our civil transportation researchers has been focused on, future mixed traffic flow control management and things like that. Not so much about the autonomous vehicle technology development and testing. But if you look at in terms of this autonomous vehicle technology development, including the the safety validation, this is really a multidisciplinary problem. It's in combination with automotive engineering, artificial intelligence, and also transportation engineering. Particularly if you want to test these autonomous vehicle in the real world and in naturalistic driving environment, either you test or train these vehicles in naturalistic driving environment. We civil engineers or transportation engineers studies how we can model this naturalistic driving environment in terms of the simulation. And so I think transportation engineering, transportation researchers has a important role in this technology development. So I want to encourage the students in the seminar and think about this technology development. We can really be part of it in terms of the development and how we can help to address the safety challenge to accelerate the development and deployment of autonomous vehicle technology. And so I mentioned a couple of papers we published in Nature series, and one of the paper for the dense learning has been published in Nature earlier this year, also featured as a cover story. Actually, if you look at it in terms of the cover, this is the city of Ann Arbor downtown, and so that's as a background imagery. And also there's a set of media coverage related with the technology we have developed. And this is a Wall Street Journal cover of some of our work. And so if you have interest, you're certainly welcome to look into these papers and in terms of detail of the technology development with that. And so with that, I'll be happy to answer any questions, and thank you for sitting through the seminar. So Dr. Ali.
Thank you very much, Dr. Luke. It is a very, very nice presentation and a very informative presentation. So we got some questions in the chat box. I'll go with those first, and then we'll see like if any other if they have any other questions or not. So the first one that I have in the chat box is, what about detecting motorcycles?
Oh, yeah. So maybe I'll go back to my slide. Yeah, so we're working on that. So for all these object detection tracking, and so we use ULO V8 right now to do the detection for vehicles, and we're also using a large model to do the auto labeling for not only vehicles but also for pedestrians and also bicyclists. And so we retrain, fine-tuning the model we have deployed to include the pedestrians and also the bicyclists. And so that's the work we are doing when we deploy this to the 21 intersections. We now have in our current system, we now have about 8 intersections with this setup. And so this one I particularly showed you has only because this roundabout has very few pedestrians. And in the current deployment, we do have the algorithm deployed to have the to detect the pedestrian and also the bicyclist as well.
Thank you, Dr. Lu, for that answer. And so the next question I have here is from Dr. Zaman. You mentioned that AVs ought to be 20% more safer than the human-driven vehicles. Where does this 20% coming from? Why it is not other like 30% or 40%?
Yeah, so that's not come from me. I was just referring to maybe I would just quit in terms of presentation, so it's easier. So I was just referring this report coming from Rand Corporation, and so they this is a paper published in Transportation Research Part A as well. If you look at into this paper, so in their study, they assume they say if we assume we want to prove that AV is 20% better, how many miles will we need to to test? And just to answer your question further, there are studies looking into what will be the acceptable safety performance for autonomous vehicles if we want to deploy this in a large scale. The argument, what I have seen, is that range from 2 times better or to 100 times better. So 2 times to 10th of power of 2. And so there's a different set of argument in terms of how does how much better is better and how much better we will need.
Sure, thank you. Another one is this appears to be focused on self-driving cars. Has any testing been done or being planned testing with commercial vehicles?
Yes. So as I mentioned, you mean commercial vehicles are trucks? Okay. No. So we have not working on trucks. So we don't at the moment we don't have a plan for testing commercial vehicles, particularly with trucks. And so as far as I know, most of the development in terms of testing has been done really by the autonomous vehicle developer themselves. Third-party testing has been very, very few. I think one of the we were among one of the first to really treating autonomous vehicle as a black box and then test that as a third party. And so that's what we're doing with this Detroit autonomous shuttle deployment project.
Thank you. So the next question I have is, are the AV assessment tests done under variable environmental conditions such as different lighting or weather?
Yeah, that need to be considered. As I mentioned, different different weather conditions, different roadway infrastructure, different behavior models. And then for ours, we utilize, because we use the roadside cameras as our data source, right? And so that the deployed roadside cameras has different, it's 24/7, so that has all sorts of weather conditions as well. So when we train the model should be able to produce these vehicle trajectories with different type of weather conditions.
Thank you. The next question we have is, globally, how do AV technologies in the US compare with the technologies in other advanced countries?
That's a topic it's a great question. It's a question that being asked many times. Comparatively, just my own, these are obviously my own opinion. So this is from a professor's opinion, right? So I think in terms of technology development, US is leading with Waymo and Cruise as the the leaders in the field. And in terms of regulatory framework, to accelerate the deployment, we are lagging. The US DOT in particular with National Highway Traffic Safety Administration, we have been relying upon self-certification with the technology. And so with regular traditional automotive scheme is essentially self-certificate. And so there's no regulatory framework available. And if you look at other countries, particularly China and also Europe, they are more advanced in terms of regulatory framework. Recent China has released one of their regulation related with autonomous vehicle deployment, particularly specification in terms of what are the documentation you have to do before you deploy, and then what tests you have to be done, and how many teleoperation drivers you have to have, and then if you result into certain accident, what type of data you have to submit. And so they have some sort of guidance framework from their Department of Transportation. And on that, I think we are more cautious, and we have been relying upon the traditional self-certification framework.
Thank you. I think the next question we have is almost same. You have already answered. So what about testing of trucks or 18-wheelers? I think you have already mentioned that. Yeah. So
the other thing I would mention is that so M-City is a small test track for for urban situations. We are 32 acres. We have a stretch of freeway. It's about 1,000 feet. You can get to about 40, 45 miles per hour. It's not designed for commercial vehicles. Not far from M-City, about 15 miles from University of Michigan. There's also American Center for Mobility and ACM test track. And that's a much larger test track. Have about 550 acres. So it's about 15 times bigger. And it has a 2 miles highway loops. And so that on that, you can do high-speed testing with commercial vehicles as well. In fact, some of our work, we use ACM for testing for high-speed situations as well. And so that's the place for high speed and also large trucks for testing.
Thank you. The next question we have here is, from an economic approach, I would think that autonomous vehicles would be much more economical for use in delivery trucks or long haul delivery.
Yeah, that was what was the argument for autonomous truck, and that's the several companies are doing that. Aurora is one of those. I think they are actually deploying that in Texas, and there are other companies making the same argument, and basically for long haul, particularly long haul trucking. And so if you have an autonomous system, and we know that the truck driver is in shortage, and this will help on that. And I would say it's not that easy either. The same problems occurs in terms of safety, the so-called curse of rarity. The long tail event is still hard to overcome, particularly a combination of not only just the occurring probability, but also in the could be a complex situation as well. So that still yet to be tested, and there's testing really going on with the autonomous trucking technology. And there's also other technologies around the globe being developed for long haul trucking as well. And so there's some argument that the technology I've seen with one human driver in the front and then several autonomous trucks in the back. And so there's some of these type of setups configuration being developed as well.
Thank you. I think one more question we have that relates to this presentation is, best guess, when will driverless cars be on the road?
Okay. Prediction into the future is always dangerous, right? So I mean that particularly with the current roadblock with autonomous vehicle technology. But myself is quite optimistic, and I do think automation is the future with advancement in artificial intelligence and some of our own work related to improving and the training and testing for autonomous vehicles. And so, although if you look into the Gartner's curve on emerging technology, autonomous vehicles right now, technology development wise, is really at the bottom, right? So it's the lowest point, and I think we are gradually coming up, and particularly with more and more investment from OEMs on ADAS system, and so and also continuous deployment and trial for autonomous vehicle technology. So I am not, I don't think I have a timeline in terms of when this will be, but I would expect in the next 10 years or so, this at least the second challenge I was talking about in terms of cursor rarity, that issue might be resolved.
Thank you. I think Sean Carlson has shared a link to on-demand self-driving shuttles. So I think So please feel free to click that link and see. So what was shared on that. So we may have a time for one more question if anyone wants to jump in at the very end and post or maybe unmute yourself and just one more question if we have. Okay, I don't see anything else. So I think with that, thank you very much for this very nice and informative presentation on automated vehicle and connected vehicles. So we really appreciate your presentation and your time with us today. Please, I will request everyone to give a virtual round of applause for Dr. Henry Liu. Very nice presentation. Thank you very much. For our audience, I have a few things to mention. So we organize this a monthly webinar. So this is an every monthly series. So we are going to start our 2024 webinar from January. So if you have any topic in your mind, or if you want to see that some speaker to participate in this webinar or short course or a workshop series, please let us know. The SPTC will try to facilitate those through this workforce development activities. And also, so we have recorded this session, so we'll share this recording, and also the slides, PDF of the slides will be posted in our website. So feel free to get access to the recording and the slides from there. And if you have indicated that you need a PDH for attending this session webinar, we will send you the PDH. Our SPTC team will work on that. And if you do not see that PDH certificate sent to you in near future, please contact us and we'll make sure you get credit for your attendance. And also, we are going to send a short survey after this webinar. So please fill out that survey. We use that information to improve our webinar to get more topic and speaker for this webinar series. So with that, thank you very much. Thank you to everyone for having us, and thank you to Dr. Henry Liu for spending time with us. We hope to see you all in our next webinar. Thank you.
Thank you.
Have a nice day.
Thank you. Happy holidays, everyone.
Thank you. Happy holidays.